Now we are discussing about monostable multivibrator using IC555. Already we discussed about IC555. So here I am representing the 8-pin IC555 and previous class I explained all those 8 pins. Now I am going to explain monostable multivibrator using IC555. If you are connecting resistor and capacitor external to the IC555, then the IC555 will be converted as a monostable multivibrator. Now this circuit will explains the monostable multivibrator. Okay, using IC555. Why I am telling it as an using IC555 is previously we discussed about monostable multivibrator using op-amps, but here we are using the IC monostable multivibrator using IC555. Now here the external components are R and C. With this combination, the total IC555 circuit will be converted as a monostable multivibrator. Now, what I am going to do is to understand the operation. First, I am assuming my Q will be high. Then what about my output? Q bar is my output, then it will be low. Why? Because if Q is equal to 1, then obviously Q bar is equal to 0. So what I am assuming is, initially I am assuming Q, the flip-flop output Q is high. When the Q is high, what happened to the transistor Q1? Whenever Q is high, the transistor Q1 drives into the saturation. Once it drives into the saturation, then the voltage across the capacitor will becomes 0. Why? Because the other end of the capacitor is connected to ground. The voltage across the capacitor is connected to 0. Okay. Now this voltage will be applied at the control voltage as well as threshold voltage. So we are having fifth pin is control voltage and the sixth pin is the threshold voltage. Now the capacitor voltage will be applied to the threshold voltage. Okay, now we are going to compare your threshold voltage with the control voltage. Why? Because we all know that the fifth pin is control voltage, and that control voltage is internally set to 2/3 VCC, and once the capacitor voltage is greater than this control voltage, then the flip-flop will be set. But what happened if the capacitor is discharged? Then obviously the control voltage will be high, then S is equal to 0. So obviously we will get the Q is equal to 0. So once Q is equal to 0, what happened to the Q1 transistor? Immediately the Q1 transistor will be cut off. Q is equal to 0. Immediately the Q1 transistor will be cut off. Then what happened? Then the capacitor will be charging through R. Okay, so the time duration for the charging of the capacitor is always depends upon R and C. Monostable multivibrator is also called as one-shot multivibrator. Why we are calling it as one-shot multivibrator is it consists of one stable state and one quasi-stable state. Whenever you applied a trigger, okay, immediately it produces a output pulse at the output. Okay, and the pulse duration is depend upon the external elements which are nothing but R and C, and after completion of that time period of the pulse, once again it backs to its stable state. Okay, now so what happened now in this case? Now I am applying a trigger pulse. Initially, I am assuming Q is equal to 1. When Q is equal to 1, then Q1 transistor is drives to saturation and the capacitor is discharges. Okay, and this threshold voltage will be applied to the the sixth, that is capacitor voltage, will be applied to the threshold voltage. Okay, now what I am going to do is, now I am applying an external trigger pulse at this second pin. Now what happened? If my external trigger pulse is greater than this, that means here the voltage will be set to 1 by 3 VCC. Already we discussed while we are discussing about IC 555, because of these three equal resistor potential divider, the voltage at the comparator 1, that is non-inverting input terminal, will be set to 1 by 3 VCC, and the inverting input terminal of the comparator will be set to 2 by 3 VCC. Now what I am telling is, if you applied the trigger pulse and if this trigger is greater than this voltage, then what happened? You will get minus Vsat, that means it is 0. So if S is equal to 1, Q is equal to 1, that means you are maintaining the previous state condition. So once if the trigger input is less than this voltage, then what happened? Because of this 1 by 3 VCC is a high value, then immediately the output of the comparator 2 will be plus Vsat. Plus Vsat means we are considering it as 1, and we applied 1 at the R. So if the S is equal to 0, then immediately Q will goes to 0. So what happened when Q is equal to 0? When Q is equal to 0, then the transistor Q1 will be cut off and the capacitor starts charging through R. Once this voltage at the sixth pin, that is nothing but the threshold voltage, which is nothing but the voltage across the capacitor, if this voltage is greater than this voltage, once again S is equal to 1. Why? Because plus Vsat will be generated, then you will get S is equal to 1, then immediately you will get Q is equal to 1. Again the process will be repeating. When Q is equal to 1, then Q1 will be Q1 drives into the saturation level, then immediately the capacitor will be discharged, and this process is repeating. Okay, but once you applied the trigger pulse, immediately the output of the monostable multivibrator generates a pulse width, and the duration of the pulse width is depends upon the elements R and C. Okay, now I think everyone will understand clearly about the operation of the monostable multivibrator. Now I am going to draw the waveforms of the monostable multivibrator. Later on we will derive the derivation for the pulse width W. First I am going to draw the waveforms. Waveforms of monostable multivibrator. First, listen. We are applying the trigger is at the second pin. Always a trigger is a negative trigger pulse. So, I am considering a trigger is a negative trigger pulse. So, which is nothing but a trigger which will be applied at pin number 2. See this one, trigger is applied at pin number 2. Now what happened? If you applied the trigger, okay now, then if this voltage, that is 1 by 3 VCC, non-inverting input terminal of the comparator 1 is greater than this trigger voltage, then immediately the plus Vsat will be generated and we will be treated it as 1. R is equal to 1, and if S is equal to 0, immediately Q will be equal to 0. Okay now, then what happened? If Q is equal to 0, then the discharge transistor or the Q1 transistor will be cut off and the capacitor starts charging. So the capacitor charging is starts, and always the charging of the capacitor will be in the form of exponential. So the capacitor will be charging exponentially. Okay now the capacitor charging exponentially, and that is the voltage we are applying at the sixth pin, which is nothing but the threshold voltage. Okay, so threshold. At the sixth pin, we are going to get the waveform is like this. When the capacitor is charging, that means when the capacitor is charging, you have to remember that one. When Q is equal to 0, then this transistor will be off, then the capacitor will be charging. When Q is equal to 0, what happened for Q bar? Obviously, the Q bar will be 1. So, it generates a positive pulse at the output, and we are getting that positive pulse at the pin number 3. Okay, and this time duration, pulse with the time duration, is depends upon the elements which we are using for the monostable multivibrator, which is nothing but R and C. These are the waveforms of monostable multivibrator. I think now you clearly understand about the monostable multivibrator. Okay, so always the waveforms are depends upon the and the capacitor charging as well as discharging is depends upon this Q1 transistor. Okay, now I am going to derive the pulse width. Okay, now always the voltage across the capacitor increases exponentially. So what is the expression for that? Vc is equal to V into 1 minus e power minus t divided by R into C. Okay, now if Vc will be 2 by 3 VCC, that means the capacitor charges to 2 by 3 VCC. Now what happened? Vc is equal to 2 by 3 VCC. Now it becomes 2 by 3 VCC will be equal to voltage, that is VCC into 1 minus e power minus t divided by RC, and this VCC cancel. 2 by 3 minus 1 is equal to minus e power minus t divided by RC. So what happened? You will get minus 1 by 3 is equal to minus t e power minus t by RC. Minus minus cancel. Then what happened to this? Apply ln. Okay, if you apply natural logarithm, ln of 1 by 3 will be equal to what? Minus t divided by RC. Then minus t will be equal to RC into ln of 1 by 3, and t will becomes minus of RC into ln of 1 by 3. So ln of 1 by 3 is equal to what? Minus 1.09. That we will be considered it as minus into minus plus. So we will get 1.1 into RC, which is taken as t. Now t is equal to 1.1 into RC. So this is the time required for the pulse width. Okay, until that time 1.1 into R value into C value. Until that time the output of the pulse width will be active. Once it completes its time, then it immediately go back to its stable state. This is about the derivation of schematic diagram of IC555 is represented like this, which doesn't shows flip-flops as well as comparator. If you are connecting external to this IC555, resistors and capacitors external to this IC555, then we will be treated it as a monostable multivibrator. Now coming to see this one, here the pin number 4 is connected to VCC. Why? Because to avoid accidental resets, we are going to connect pin number 4 to VCC. Generally, if you are connecting pin number 4 to ground, then what happened? Then it overrides the functions of IC555. It acts as a on and off control switch for the IC555. So, to avoid the accidental reset, we are going to connect the fourth pin to VCC. And if you observe the fifth pin, which is nothing but the control pin, to eliminate the noise filtering on the control voltage, we are going to connect a small capacitor to the ground. Because of this, the noise at the control voltage signal will be eliminated, and the resistances and the capacitance, see, they are decides the width time duration of the output pulse. This is schematic diagram of monostable multivibrator. Applications of multivibrator. First application is monostable multivibrator will be used as a frequency divider. How can you express the monostable multivibrator is used as a frequency divider? We all know that whenever a trigger pulse is applied to the monostable multivibrator, it produces the positive pulse with positive pulse output at the output side. So, by making the output pulse width time interval is greater than the time period of the input pulse width, we can treat this monostable multivibrator as a frequency divider. How can we construct the monostable multivibrator as a frequency divider? For an example, here I have drawn the input and output waveforms for the frequency divider. First, I am assuming the output pulse width time interval, this small t, is greater than the input time period, that is capital T. So, whenever you are applying a negative edge triggered pulse at the triggered input, immediately it produces the positive pulse width at the output side. So, even if you are coming to the second negative edge triggered pulse, because of time interval of the output is greater than the time period of the input signal, it doesn't perform any operation, and after completion of this time period, once again it go back to its original state, and the monostable multivibrator again will be operated at the third negative edge triggered pulse. That's why again at the third negative edge triggered pulse, it is going to be produced the positive pulse output. So from this, what we can conclude is, for every two trigger pulse inputs, we are getting only one output pulse width at the output side. That's why we are treating the monostable multivibrator as a frequency divider. In this case, the monostable multivibrator will be used as a pulse width modulation. So this figure represents the pulse width modulation. Generally, if you observe this figure, it looks like a monostable multivibrator, no doubt. For the IC555, if you are connecting externally R and C, then it becomes a monostable multivibrator. So, to act as a pulse width modulator, what you want to do is, you have to apply the modulating signal at the control voltage input. Generally, the control voltage input of the monostable multivibrator is internally fixed to 2/3 VCC value. Once you apply the control modulating signal at that control voltage signal, then the threshold level of the control voltage will be varying. So automatically the time required to charge the capacitor as well as to discharge the capacitor is also varying. So obviously we will get the different pulse widths will be generated at the output side. So here I am showing the input and output waveforms of the pulse width modulator. Here upon the application of the trigger pulse, generally the monostable multivibrator generates the output signal. Here the modulating signal will be applied at the fifth input. So internally the control voltage is fixed to 2/3 VCC, but upon the application of this modulating signal for the positive pulses, the control voltage will be increases, as well as for the negative pulses the control voltage will be decreases. Here if we have seen this circuit, for the positive voltages we will get the large pulse width value, as well as while it is decreasing the pulse width, automatically it decreases. While we are decreasing the modulating signal, the pulse width will be decreases, and when it is a low modulating signal, then the pulse width is also decreases very low value. So because of this modulating signal, whenever the modulating signal is increases, then the time required to charge the capacitor will be increases, then the pulse width duration will be increases, and whenever the modulating signal is decreases, then obviously the control voltage will be decreases and the time required to charge the capacitor will be decreases. Because of this we are getting the different pulse width at the output side. This is the application of monostable multivibrator is linear ramp generator. When the capacitor is linearly charged with a constant current source IC, then the linear ramp is generated. This concept is used in the linear ramp generation. Here for the generation of the constant current source, we are going to be used the current mirror circuit, and the current mirror circuit is constructed with the help of transistor Q and diode D. With the help of transistor Q and diode D, we are generating the constant current source, that is IC will be equal to VCC minus VBE divided by R, which is nothing but generation of constant current source. Here VBE is nothing but VD, so we may also represent it as VCC minus VD divided by R. Okay, so that is the voltage. This is the voltage we are applying for the generation of the constant current source IC, and this constant current source is used to charge the capacitor towards plus VCC. While the capacitor is charging, once the threshold value is reaches to 2/3 VCC, then what happened? The comparator 1 will becomes the comparator 1 generates the output as plus Vsat, and it will be applied at the SR flip-flop S input, and we will get the output Q as 1. When Q is equal to 1, then it immediately drives the Q1 transistor into the saturation. Once the Q1 transistor is into the saturation, then immediately the capacitor starts discharging. Once the capacitor starts discharging, and the value of the 1/3 VCC will be greater than the trigger voltage, then immediately the comparator 2 will becomes high value, and which resets the flip-flop, and Q will becomes 0. Once Q is equal to 0, then the transistor Q1 will be off and capacitor starts charging. So this is the way we are going to charge and discharge the capacitor with the constant current source. And if you are observe the charging and the discharging of the capacitor, it will take high amount of the time to charge the capacitor, and it will take a very less amount of the time to discharge the capacitor. So obviously we are taking that the charging time is nothing but the linear ramp generator, but generally we will be considered the total time T is equal to charging time plus discharging time, but TD will be very small when compared with the TC, so we obviously consider T is equal to TC, and the total time required for the charging of the capacitor will be equal to VCC into C divided by 3 into IC, and here I am representing the input output waveforms. Here it is the output voltage and this is the ramp generation. Why? Because with the continuous current source, while the capacitor is charging, then it produces the ramp signal. That's why it produces the ramp signal for the charging as well as for the discharging. Okay, now very well known that when it is a output is a positive value, then the charging of the capacitor will be takes place, and the output is a negative value and the discharging of the capacitor will be takes place. If you observe from the circuit also, the discharging time will be very less when compared with the charging time. Other application of the monostable multivibrator is nothing but missing pulse detector. This circuit represents the missing pulse detector. Here when the input signal is at ground level, so what happened? The emitter diode of the transistor is forward biased, which clamps the capacitor voltage to 0.7 volts. So, and it forces the output as a high level state, and whenever the input signal is equal to 1, then the transistor T is cut off and the capacitor starts charging, and before the 555 is not complete its timing cycle, if the input is again goes slow, then immediately the capacitor voltage is again reset to 0.7 volts. Or if the 555 timer doesn't go slow before completion of its timing cycle, then it enters into the normal operation and it produces the output signal as a low signal. And now we are going to explain the waveforms of this missing pulse detector. From these waveforms we clearly understand the missing pulse detector. The timing interval is adjusted longer than the time period of the input signal, and because of the continuous low pulses time period, which is less than the timing interval, which does not allow the capacitor to charge up to 2/3 VCC. In case of the missing pulse detector, once the capacitor is charging to 2/3 VCC, it immediately forces the output voltage to 0. Generally, this missing pulse detector circuit is used to detect the heartbeat. Another application of the monostable multivibrator is ppm generator. In this pulse position modulation, the position of the pulse is varying and the width and the amplitude of the pulse is keep constant. Here the position of the pulse with reference to the position of the reference pulse is changed according to the instantaneous sampled value of modulating signal. So here the ppm generator circuit consists of differentiator, which is nothing but combination of R and C, and a diode consists of monostable multivibrator. This total circuit will be treated as a ppm generator. Here first at the input we are applying the PWM pulses, which is nothing but these pulses. the width will be changing and the amplitude and the position is keep constant. Those are pulse width modulated pulses applied at the triggered input. Before applying to the trigger input, it will be passed to the differentiator, and the differentiator differentiates this signal according to the leading edge and trailing edges. That means it produces positive spikes as well as negative spikes, and the diode is bypassing the positive signals and which produces the negative pulses at the triggered input, and now this trigger is used to generate the pulse position modulating signals according to the instantaneous modulating signal, which is nothing but the PWM pulses. So what happened in this case is the pulse is means the width and the amplitude is constant, and the position of the pulse is varying, that depend upon the instantaneous sampled modulating signal, in this case which is nothing but the PWM signal. It will be used as a frequency divider, and the monostable multivibrator is used to generate the PWM pulses, and the monostable multivibrator is used as a missing pulse detector, and the monostable multivibrator is used as a linear ramp generator. Last but not the least is monostable multivibrator is used as a PPM generator. All these 5 applications of the monostable multivibrators are very important in the exam point of view also. So whenever they are asking you to write about the monostable multivibrator and its applications, first of all you have to explain the monostable multivibrator, and also you have to explain the input and output waveforms of the monostable multivibrator. Along with you have to derive the pulse width derivation. Later on you should express all these applications of monostable multivibrator. We are going to discuss about astable multivibrator using IC555. Last class we discussed about monostable multivibrator using IC555. There the monostable multivibrator is also called as one-shot multivibrator, but in this case the astable multivibrator is called as free running non-sinusoidal oscillator. Coming to this figure, this circuit represents IC555 is used as a astable multivibrator. Here the threshold input and the trigger input are connected together, and for this astable multivibrator we will not apply any external trigger pulse, and the astable multivibrator doesn't consist of any stable state. It consists of 2 quasi-stable states, and the circuit changes its states alternately. Okay, now for the understanding of the operation of this circuit, first I am assuming the output of the flip-flop Q will be high. So if the flip-flop is high, then it drives the transistor Q1 into saturation. Then it discharges the capacitor. What happened when it discharges the capacitor? Whenever it discharges the capacitor, that voltage will be applied as a trigger voltage, and this trigger voltage is less than this voltage, then immediately comparator 2 produces the output as a plus Vsat, and that will be considered as 1 and which will be applied at R. And obviously if R is equal to 1, then S will becomes 0. So Q will becomes 0. Once Q is 0, then what happened? Then Q1 is cut off. Then the capacitor starts charging through RA, RB. So this charging of the voltage, the charging capacitor voltage will be applied as a threshold input of the comparator 1. It will be comparing with the 2/3 VCC. Once this threshold voltage is greater than this 2 by 3 VCC, immediately the comparator 1 produces the output as plus we said, which is nothing but S is equal to 1. If S is 1, then obviously R is equal to 0. Then immediately Q will becomes 1. Once Q is becomes 1, then what happened? Once again, the transistor Q1 will be drives and the transistor Q1 drives and it goes to the saturation or it discharges, and immediately the capacitor will be discharges. And once again we are applying the discharging capacitor voltage as a triggering input. So when Q is equal to 1, then obviously Q bar is equal to 0. What happened when Q is equal to 1? When Q is equal to 1, then the capacitor will be discharged. At that time the Q bar is equal to 0. So when your output is low, the capacitor is discharging. Suppose when Q is equal to 0, then what happened to your Q bar? Q bar is equal to 1. When Q is equal to 0, then the transistor will be cut off and the output is high. That indicates the capacitor going to charge. So with this circuit, we are going to draw the waveforms of the unstable multivibrator. Here I am not representing any external trigger pulse. Why? Because the unstable multivibrator doesn't require any trigger pulse to operate. So here I am considering the charging of the capacitor voltages, that is 1 by 3 VCC when it is discharges and 2 by 3 VCC whenever it is charging. Just now I explained what happened when Q is equal to 0 and what happened when Q is equal to 1. When Q is equal to 0, this one will be off. So Q bar is equal to what? High. So immediately the capacitor will be charging through RA and RB. So here I am representing the charging of the capacitor. And listen carefully, while the capacitor is charging, it is charging through RA and RB. While it is discharging through RB. And here I am showing the exponential form for the increasing of the capacitor as well as for the discharging of the capacitor. Now we are going to discuss about duty cycle. If you observe the waveforms of the unstable multivibrator, the charging time constant is greater than the discharging time constant. So obviously the output is not a square wave. It is a variable on time and it consists of variable off time. So on time is not equal to off time. So we are getting a non-symmetrical output waveform because of variable charging time as well as discharging time. So here we are treating that charging time is taken as TC and discharging time will be considered as TD. So the charging of the capacitor will be because of RA and RB. So TC will be taken as 0.693 into RA plus RB into C, and the discharging time will be generated because of RB into C. So 0.693 into RB into C. The duty cycle is nothing but the on time divided by the total time period. So what is total time period? So T is equal to TD plus TC. Okay, on time is nothing but TC, charging time. So percentage of D is equal to TC divided by T into 100. So what is TC? 0.693 into RA plus RB into C divided by 0.693 into RA plus 2RB into C into 100. Yes or no? Which is nothing but percentage of duty cycle. So once we cancel these two terms, then we will get RA plus RB divided by RA plus 2RB into 100, which is nothing but the percentage of duty cycle. Once we know the total time period, then we can easily calculate the frequency of oscillation. In the unstable multivibrator, we are mainly concentrating on frequency of oscillations. How can you represent the frequency of oscillations? F will be taken as 1 by T. What is 1 by T? 1 by total time period Tc plus Td, which is nothing but 0.693 into Ra plus 2 into Rb into C. So 0.69, 1 by 0.693 is nothing but 1.44 divided by Ra plus 2Rb into C hedges, which is nothing but the frequency of unstable multivibrator. Coming to the application of the unstable multivibrator. Unstable multivibrators is used as a square wave generator. But generally, if you observe the waveforms of the unstable multivibrator, their T on is greater than T off. That means charging time period is greater than discharging time period. So we will not get the symmetrical waveform at the output side because of charging time greater than the discharging time period. So to obtain the symmetrical waveform, that is exactly 50% of the duty cycle, if you want to generate, you have to modify the unstable multivibrator circuit. So here this is the modified unstable multivibrator circuit for the generation of square wave. So here what I am doing is, in this case the capacitor is charging through Ra and diode, and the capacitor is discharging through Rb. While adjusting, the Rb value should be equal to Ra plus diode value. Then it will possible to generate the 50% of the duty cycle. That means exact 50% of the duty cycle will be generated only when Rb value will be equal to Ra and diode value. So we will get the exact 50% of duty cycle. And here I am representing the waveforms for the generation of this 50% of duty cycle. If you observe this waveform, here the T on and T off will be equal. Here this charging time period will be because of Ra and diode, and the discharging time period will be generated because of Rb and C. Okay, so what I am telling is, while you are adjusting the Rb value will be equal to Ra plus diode value, then it is possible to generate the 50% of duty cycle, and the variable of the resistance is generated because of the potentiometer. So by using the potentiometer, you can easily adjust the value of Rb will be equal to Ra and diode value. Then only we will get the exact 50% of duty cycle. Main application of the unstable multivibrator is voltage controlled oscillator. Generally, we will be used the unstable multivibrator as a voltage controlled oscillator. If you observe this circuit, it will be used as a voltage controlled oscillator, and this circuit consists of two resistors and capacitors which are externally connected to IC 555. Then it will be treated as an unstable multivibrator. So we will be used this circuit as a voltage controlled oscillator, and we all know that the internal control voltage of the unstable multivibrator is fixed to 2 by 3 VCC. In most of the applications, we doesn't require the external control voltage, but in this case we are requiring the external control voltage for the generation of different frequency of different time period signals. So here the external control voltage is applied with the help of potentiometer. So with the help of potentiometer, we applied the external voltage at the control voltage. Because of this, the upper threshold limit value for the comparator 1 will be changes. That means the charging time of the capacitor will be changes. Not only the charging time, the discharging time period of the capacitor is also changes. Why? Because here the sixth and the second pin will be connected together. Generally modulating signal is high. Then what happened? Then it takes high amount of the time to charge the capacitor as well as discharge the capacitor. If the time period is high, what about the frequency? The frequency will be decreases. If the modulating signal is low, then what happened? It takes less amount of the time to charge the capacitor as well as discharge the capacitor. And if the time period is less, then what happened? Obviously the frequency will be high. So this is the way we are going to generate the variable frequencies. That's why the stable multivibrator will be used as a voltage controlled oscillator. Here the stable multivibrator will be used as a FSK generator. How can we generate the FSK signals by using a stable multivibrator? FSK is nothing but frequency shift keying technique. The binary signals, which is nothing but ones and zeros, the binary signals are transmitted by shifting the carrier frequency, and one fixed frequency will be representing for 1 and another fixed frequency for representing the binary symbol 0. So this type of shift technique is called as frequency shift keying technique. By using this technique, we can transmit the binary data. Here, what is going to be happen? While you are applying the binary data to the stable multivibrator, so whenever your input is high, then what happened? If your input is high, then the transistor T1 will be off. Then this circuit will be acts as a normal stable multivibrator. Why? Because here the T1 is off, then there will be no connection from RP to this point. So it will be act as a normal stable multivibrator. So the total frequency F will be represented as 1.44 divided by R1 plus 2R2 into C. Okay. If the input signal is low level, so what happened? If it is low level, then the transistor T1 is on. Then this RP resistor will becomes parallel to R1. So what happened for the final frequency if RP parallel R1? So the final frequency will be represented as F is equal to 1.44 divided by R1 parallel RP plus 2 into R2 into C. So these are the frequencies generated when binary signal is 1, when the binary input signal is 1, and when the binary input signal is 0. So this is the way we are going to generate the FSK signals. That's why we are calling it as a stable multivibrator is also called as FSK. Stable multivibrators are used for generating the duty cycle in between 50% to 100%. Sometimes we require the variable duty cycles, that is less than 50% is also required. Previously, in one of the application, we have seen that the stable multivibrator is modified to generate the square wave output. So here also it is similar to that circuit, but here in the previous case, that is whenever you want to generate the output as a square wave, there we connect the diode D across the resistance RB, but in this case we connect the diode D across R2 and R3. Here the R2 resistor is the variable resistance and which can be adjusted with the help of potentiometer. So because of this R2 resistance, the charging time as well as the discharging time of the capacitor will be varying. If the charging time and the discharging time is varying, automatically the frequency of oscillations is also varied. So what happened for the charging time? So TC will be equal to 0.693 into R1 plus part of R2. Yes or no? Part of R2 into C. So which is required for charging the capacitor. And what about the discharging time period? Discharging time period is equal to 0.693 into R3 plus part of R2. That is remaining part of R2. Remaining part of R2 into C. Here while it is charging, that is R1 plus part of R2 and diode. Here I am not mentioning the diode, don't confuse about that. So 0.693 into C into R1 plus part of R2 for charging time period, and TD is equal to 0.693 into R3 plus remaining part of R2 into C. So what about T? T will be equal to TC plus TD, which is nothing but the total time period required for the charging as well as the discharging. So what about the total time period? 0.693 into R1 plus R2 plus R3 into C. So what about F? F is equal to 1 by T. So 1 divided by 0.693 into R1 plus R2 plus R3 into C. So we will get 1.44 divided by R1 plus R2 plus R3 into C, which is nothing but the frequency. Total frequency of the stable multivibrator. By using this circuit, we can generate the variable duty cycles. That means we can generate the duty cycle less than 50% as well as we can generate the duty cycle greater than 50%. But listen carefully, the normal stable multivibrator always generate the duty cycle in between 50% to 100%. First of all, for the generation of minimum duty cycle, here I am considering the position of the potentiometer is at A. So position of potentiometer at A. Then what happened for the charging time period as well as the discharging time period? So when the position of the potentiometer is at A, then the charging time period is R1 and diode. So TC will be equal to 0.693 into R1 into C. In this case, part of R2 will be 0. Why? Because the entire R2 will be connected to R3. So the discharging time period TD will be taken as 0.693 into R2 plus R3 into C. So the percentage of duty cycle is equal to R1 divided by, what about this total time period? R1 plus R2 plus R3, which is used for generating the duty cycle less than 50%. That means minimum duty cycle will be obtained when the position of the potentiometer is at A. So while using this circuit, we may generate the percentage of the duty cycle should be less than 50% when the position is at A. Now tell me what happened if the position is at B. If the position is at B, then the part of R2 will be removed from R3. The total R2 will be added to R1 only. So when the position of the potentiometer at B, so charging time period will be equal to 0.693 into R1 plus R2 into C, and the discharging time period is equal to 0.693 into R3 into C. So the percentage of D will be equal to R1 plus R2 divided by R1 plus R2 plus R3. So this is the maximum generation of duty cycle when the potentiometer is adjusted to point B. Okay, so if the potentiometer is adjusted to point A, we will get the minimum duty cycle, which is nothing but less than 50%. If it is connected to point B, then we will get the maximum duty cycle, which is nothing but this. So by using this circuit we can generate the variable duty cycle.